Namaste. Welcome to the lecture series on the subject Applied Thermodynamics, Module 3, Vapor Power Cycles. This is lecture number 9. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So in this lecture, we will continue to solve a few more problems on Rankine cycle, and this is the last lecture on this module. So let us discuss this problem number 8. An ideal Rankine cycle with reheat is designed to operate according to the following specification. Pressure of steam at high pressure turbine 20 megapascal, temperature of steam at high pressure turbine inlet 550 degrees Celsius, temperature of steam at the end of reheat 550 degrees Celsius, pressure of steam at the turbine exhaust 15 kilopascal, quality of steam at turbine exhaust 90%, determine the pressure of steam in the reheater, ratio of pump work to turbine work, ratio of heat rejection to heat addition, cycle efficiency. Okay, so it is ideal Rankine cycle with the reheat. So it is a reheat cycle. So the pressure of steam at high pressure turbine, HP turbine inlet is 20 megapascal, and temperature at the turbine inlet, high pressure turbine inlet, is 550 degrees Celsius. So steam at the end of reheat. So after reheat, once again it is heated to 550 degrees Celsius, and steam at the turbine exhaust is 15 kilopascal. So final pressure is 15 kilopascal. Quality of the steam at the turbine exhaust is 90%. So you have to find out the pressure of steam in the reheater. So second intermediate pressure is not given here, so that you have to find out. Ratio of pump work to turbine work, ratio of heat rejection to heat addition, and cycle efficiency you have to find out. So let us represent this on the HS diagram. So one is the inlet to the boiler, 2 is the exit of the boiler or entry to the HP turbine. So 2 to 3 is the HP turbine, right? So 3 to 4 is the reheat. So these two temperatures are same, T2 and T4, they are same, and then second stage expansion is 4 to 5 till the pressure is 0.15 bar. So it is given 20 megapascal, that is P2 or P1, both are same because 1 to 2 is a constant pressure heat addition process. So it is 200 bar, T2 is 550 degrees Celsius, T4 is 550, P5, that is P5 you can take, or you can take this as P1, P2, P3, like that also you can take. Now with respect to 0.5 it is taken, so P5 is 0.15 bar, X5, so dryness fraction at 0.5 is 0.9. Now let us make use of a Molar chart. So locate point 2, that is at 200 bar and 550 degrees Celsius. You will find out H2 as 3370 kilojoules per kg. Now since you don't know the intermediate pressure, right, so let us locate 0.5 first. So 0.5 is a dryness fraction of 0.9 and pressure 0.15 bar. So if you locate this 0.5, intersection of 0.15 bar and X5 is equal to 0.9, you will get H5. Now from H5, noting down H5, from 0.5 you go up till it intersects 550 degrees Celsius line. Somewhere here 550 degrees Celsius line is there because temperature at 4 is 550 degrees Celsius. So that is nothing but H4. Now note down the pressure passing through that point. You see this vertical line and this 550 degrees Celsius, you will get 0.4. Note down the pressure passing through that point and then come along that pressure line, okay, and till it intersects a vertical line from 2. So that point is 3. So that is nothing but sorry, H3. So note down these values first. Now from this Molar chart, so you can find out P3 is equal to P4 is equal to 28 bar. That means once you go from 0.5 vertically up to intersect a 550 degrees Celsius line, so then pressure will be 28 bar, which is also equal to pressure at P3. So from 2 you have to come vertically downwards till it intersects 0.3 on 28 bar line. Okay. Now H6 you have to find out using steam tables. So at 0.15 bar, so 0.15 bar, so it is 226 kilojoules per kg, and you know the formula for the pump work, WP is equal to V into integration of dP. So this is a VF at 0.15 bar, so it is 0.0010140, correct, into pressure difference 1 to H1 or P1 minus P6, that is 200 minus 0.15 bar, so into 10 to the 5 divided by 10 to the 3 to convert that into kilojoules. So it is 20.26 kilojoules per kg. Also you know that WP is equal to H1 minus H6. So H1 is equal to WP plus H6. So you will get it as 246.26 kilojoules per kg. So with this, you see, this is the first step of any problem on vapor per cycle, wherein you have to note down the enthalpy at various points. Okay. Now pressure of the answer. Now let us answer the questions one by one. So pressure of steam in the reheater. So that's already we found out from the Molar chart. It has 28 bar. Turbine work. So since there are two turbine works, HP turbine 2 to 3 and LP turbine 4 to 5. So it is H2 minus H3, HP turbine, H4 minus H5, substitution, simplification. You will get turbine work as 1740 kilojoules per kg. And already you know calculated the pump work in the previous slide, so you can find out the ratio of the pump work to the turbine work. So you'll get it as 0.0116 or 1.2%. That means pump work is 1.2% of turbine work. That means a very small quantity of turbine work is utilized for the pumping work. Now coming to the heat rejected, so you know that 5 to 6 is the condensation process in the condenser. So heat loss is H5 minus H6, so which comes around 2184 kilojoules per kg. And heat addition, as all of you know, in a reheat cycle, 1 to 2 is the primary heat addition process and 3 to 4 is the reheat. Okay, so two heat terms, H2 minus H1 and H4 minus H3, after substitution and simplification you will get it as 3924 kilojoules per kg. So the ratio of heat rejected to the heat addition you are supposed to calculate, which comes around 0.5565 or 55.65%. Look at the loss here. So heat loss is around 55.65% of heat addition. And coming to the cycle efficiency, which is nothing but W net by Q total, that is Q primary plus Q reheat. So W net is nothing but W turbine minus W pump. So this is the total Q in, right? So you'll get it as 0.4383 or 43.8% as the reheat Rankine cycle efficiency. Okay. Now let us solve this problem. An ideal regenerative cycle on. Now this is problem on regenerative cycle. Maybe the first problem we are solving on regenerative cycle, which operates with dry saturated steam. That means the entry point to the turbine is the dry saturated steam. The maximum and minimum pressures are 30 bar and 0.04 bar. That is a boiler pressure and the condenser pressure. The plant is installed with a single mixing type feed water heater. So this is a mixing type feed water heater where the steam bled from the turbine and the condensate water or the feed water, so they are mixed. The bled steam pressure is 2.5 bar. So steam is bled at 2.5 bar pressure. You have to find out the mass of the bled steam, the thermal efficiency of the cycle, and specific steam consumption in kg per kilowatt hour. Now if you represent this problem on a TS diagram and the pH diagram, or HS diagram, sorry, rather, TS and HS diagram. So 2 is the saturation point. It is given the steam entering the turbine at the saturated steam. So then at point 3s, so some steam is bled, which is taken as m kg. At this point the pressure is 2.5 bar. So from 30 bar, when the expansion takes place to 2.5 bar, so m kg of steam is bled from there. So remaining steam, that is 1 minus m kg, expands from 3s to 4s to a pressure of 0.04 bar, right? So that is the condenser pressure. So then this is a condensate and this is the first pump here. Then mixing is there, 3s and 6s, the bled steam at 3s and the condensate at 6s, they will come and mix in the feed water heater. So 7 is the what you call the after mixing in the feed water heater. Then it is pumped back to the boiler pressure at 1s, which is equal to 30 bar, and it is heated to turbine inlet pressure of 30 bar and dry saturated condition. So this is the Molar chart or the HS diagram of the same problem. Okay. Now Now let us note down the data. So P1 is equal to 30 bar, P2 is equal to 2.5 bar, all these things with reference to this TS and HS diagram. So you can name it P1, P2, P3, PB. So you see, naming is your choice. Okay, P3 is 0.04 bar. Now from steam tables, for dry saturated steam at 0.2, that is at 30 bar, H2 is nothing but Hg, so which is 2802.3 kilojoules per kg. So 30 bar pressure, let me check the steam table. 30 bar pressure, so Hg value is 2802.3 and Sg value is 6.1838 kilojoules per kg per Kelvin. So H2 is Hg, S2 is nothing but Sg. Okay, but S2 is equal to S3s. So S3, 3 means what? That is nothing but SF3 plus X3 into SFG3. So these 2 points, so this is SF3. Okay, so you can write separate formula also. So X3 and this is SFG3 for your information. Okay, since I use the formula directly, I substituted there. So it is actually, this is S2. Okay, this is SF3 plus X3S SFG3. So that is nothing but S3S. So if you substitute and simplify, you will get X3S, that is the dryness fraction after the at the bleeding point is 0.841. So once you find out X3S, so you can find out H3S using this formula. So H3S is nothing but HF3, right? So this is again 2.5 bar. You see, this is corresponding to, you see here also SF3 and SFG3. So they are corresponding to 2.5 bar. Note down, because 0.3S is on 2.5 bar line. Very, very important. So I hope by this time you will be very much familiar with this. So here also HF3 plus this is X3S. This is X3S, that is 0.841, and this is HFG3. HFG3. So here HF3 and HFG3. So once again, it has to be taken from the table at 2.5 bar. Okay, very, very important point to be noted. And after substitution and simplification, you will get the H3S value as 2452.68 kilojoules per kg. Also we know that S2 is equal to S4S. So on the similar line, you have to calculate X4S. So here this is SF4S or SF4. Yes, if you want, I can write. Okay, this is SFG4 or SFG4S, you can write. So similar previous slide also same thing. S suffix I didn't write. Okay, so using this, now this is at 0.04 bar pressure, so important. So this is at 0.04 bar pressure. So that is where you have to be extremely careful, noting the values of SF, SFG, HF, HFG. So you'll get X4S as 0.715, right? And now you calculate H4S. So once again, this is HF4 or HF4S plus X4S. This is X4S, just now you calculated. Okay, and this is HFG4S. Okay, HFG at 4S. This is again at 0.04 bar. Very, very important, because if you note down at some other pressure, so you'll end up with the wrong answer. So with this, you see, you found out H2 directly from the steam table. You calculated X3S and you calculated H3S. Then you calculated X4S and you calculated H4S. So this is how you have to proceed. Okay. Now to find out H5 value, as all of you know, H5 and H7, you see, they are on the saturated liquid point line. Okay, saturated liquid line. So H5 is nothing but H5 at 0.04 bar. So that is what, at 0.04 bar, H5 is equal to HF, that is 121.4 kilojoules per kg. And V5 also you have to note down to calculate the pump work. So pump work, condensate pump work, that is 5 to 6S, is nothing but H6S minus H5 is equal to V5 into P2 minus P3. Because this is taking place, you see, 5 to 6S. 6S is on 2.5 bar line. Okay, and 5 is on 0.04 bar line. So pressure difference is 2.5 minus 0.04 bar. Okay, and after substitution and simplification, you will get the pump work as 0.247 kilojoules per kg, and after simplification for H6, which is nothing but H5 plus pump work, you will get as 121.65 kilojoules per kg. On similar grounds, you have to calculate H1S, which is nothing but H7 plus V7 into P1 minus P2. You see, H1S is nothing but H7 plus pump work. Pump work is nothing but V7 into P1 minus P2 into 10 to the power 5 divided by 10 to the power 3. So H7, once again, it is nothing but HF value. This is nothing but HF value at 2.5 bar. So H7 is nothing but HF. Okay, HF at 2.5 bar. Sorry. .5 bar. Okay. So you'll get H7. So H7, sorry, H1S, H7 is 535.4, 2.5 bar pressure. So it is 535.4, correct. So H1S, you will get it as 538.34 kilojoules per kg. So now it's very important to find out the mass of the blood stream, because now what you did, you found out H2, H3S, H4S, H5, H6S, H7, H1S. Okay, our job is almost completed, because we noted the enthalpy at various points. Now let us take the apply the energy balance to the feed water heater. So feed water heater is entry point, one is 6S, one is 3S, which is steam, and 6S is the condensate water, and outlet of the feed water heater is 7. So 1 kg at 0.7, so 1 into H7. But at H3S, only m kg of the steam is bled at H3S, so m into H3S, and remaining 1 minus m kg is passing and entering at 6S, so 1 minus m into H6S. So very simple. So m into H3S plus 1 minus m into H6S is equal to H7. So you can write formula for m, simplifying that. So it is H7 minus H6S divided by H3S minus H6S, and you will get it as 1.177 kg per kg of steam. So from every 1 kg, 0.177 kg is bled at 0.3S. So this m is only 0.177 kg. So remaining 1 minus 0.177 kg, so that goes to the condenser. Now thermal efficiency. So as you know, turbine work. So now 2 expansion you have to find out, 2 to 3S. So only 1 kg of complete 1 kg of steam expands here from 2 to 3S. But here remaining part 3S to 4S, you know that 1 minus m kg is undergoing expansion. So it is 1 minus m into H3 minus H4S. So this is very, very important. So that is why you have to calculate m before you proceed to calculate the turbine work. So after substitution and simplification, you will get the turbine work as 835.67 kilojoules per kg. Now let us calculate the pump work. So there are 2 pumps. Can you see here? 5 to 6S is the condensate pump, and 7 to 1S is the feed water pump. So here condensate pump is handling only 1 minus m kg. So that is why first term it is 1 minus m into H6S minus H5. Whereas at 0.7 this condensate 1 minus m and blood stream of m, so they combine 1 minus m plus m, so it becomes 1 kg again. So 1 into H1S minus H7. So this is very, very important. Okay. So if you substitute and simplify, you will get the total pump work as 3.146 kilojoules per kg. So already you calculated individual pump work, right? But that is different. Now the total pump work you have to calculate like this. Now W net is nothing but WT minus WP, so which is nothing but 832.52 kilojoules per kg, and heat supplied is nothing but H2 minus H1S, so that is for complete 1 kg. So you will get it as 2263.96 kilojoules per kg. Finally, to conclude, let us calculate the efficiency W net by QH. So we'll get it as 36.8% and specific steam consumption as 4.324 kg per kilowatt hour. So with this I conclude this lecture number 9 as well as this entire module 3 of vapor cycles. I request all my dear students to work out these problems. Don't just listen to the video. Work out, and if you have any problems, if you have inquiries, or if you want any improvements in my lecturing, so you can email it to that email ID given in the template. Okay, thank you.